This video covers rotational kinetic energy. Rotational kinetic energy is energy due to circular motion of an object. So let's say an object is rotating about its center. Now, its center itself is not moving, so it's rotating about a fixed axis. So if we know its kinetic energy is 1/2 mv squared, we can actually rewrite this equation because v, our linear velocity or tangential velocity, is equal to r omega. So we can replace v with r omega, and this becomes r omega squared. Well, if you notice, this becomes r squared omega squared. This right here is moment of inertia. So rotational kinetic energy is 1/2 times moment of inertia times omega squared. So let's look at this example. We have a 1.2 kilogram disc with a radius of 10 centimeters rolls without slipping. The linear speed of the disc is 1.41 meters. So here we have an object that is rotating and moving forward. So we can look at our total kinetic energy as being the linear kinetic energy. So this is the energy it would have if it was sliding across the table. And again, this is the energy that it has because it is also rotating. So you always include this piece if your axis is rotating or moving, axis is moving. And you include the second piece if your object is rotating. So we have a 1/2 m, our velocity is 1.41 meters per second squared, plus a 1/2, and for a disk we have a moment of inertia of 1/2 mr squared. This comes out of your reference table. And omega can be replaced with v over r. So we actually have this v as well. So once you simplify and put in all of your values, you should get a total kinetic energy of 1.79 joules. This example is also a very common example. It says a ball rolls without slipping down incline A, starting from rest. At the same time, a box starts from rest and slides down incline B, which is identical to incline A, except that it is frictionless, which arrives at the bottom first. So we can start with our conservation of kinetic energy or conservation of energy equations. At the very top, we can say that we have 0 velocity. We also have 0 rotational kinetic energy at the beginning, so all of our energy is gravitational potential energy. At the end, we're not going to have any more height, so we won't have any more gravitational potential energy, but we'll have kinetic coming from our linear velocity and rotational kinetic energy coming from our rolling. This box that slides will have 0 kinetic energy at the beginning and 0 potential energy at the end. So that means that our box that slides is going to arrive faster at the bottom of the incline than an object that rolls. And the reason for that is because all of its energy is no longer being transmitted only to kinetic, but it has to be shared with rotational kinetic energy. So we're just going to set this problem up. It says a ball of mass m and a radius r starts from rest at a height of h and rolls down 30-degree slope. What is the linear speed of the ball when it leaves the incline? Assume that the ball rolls without slipping. So at the beginning, we have entirely potential energy. At the end, we're going to have kinetic energy because we're moving linearly, and rotational kinetic energy because it's rotating. Now, we can replace omega with v over r, and we need to make sure that we square it. And our moment of inertia for a ball, we can say is 2/5 mr squared. Again, these numbers can come out of your reference sheet. So here I have a velocity that I can factor out, and I can also factor out a 2, or 1/2 from both sections, and I'm left with m plus 2/5. Our r's will cancel out here. 2/5 m is equal to mgh. So here you can see that our mass actually doesn't affect our equation at all. So our masses will cancel out, and we're left with gh is equal to v squared over 2, 1 plus 2 over 5, which we can find a common denominator, which simply gives us a velocity. Let's go ahead and simplify this right-hand side, of 7 over 5, which gives us a velocity squared of 10gh over 7, and then square root. So we can put all of our values in and get a number for that. Now this last example is the one most commonly seen on an AP exam. It says two blocks having different masses m1 and m2 are connected by a string passing over a pulley. The pulley has a radius r and a moment of inertia I about its axis of rotation. The string does not slip on the pulley and the system is released from rest. Find the translational speeds of the blocks after block 2 descends through a distance h. Find the angular speed of the pulley at that time. So to start this problem, our picture actually looks a little bit different from what you see here. We have a mass m1 that's closer to the ground, passes over my pulley system, and then my mass 2 is above the ground, a distance h above. So we can say that the energy it begins with is m2gh. All of the energy is gravitational potential energy at the very beginning because it is released from rest. And then our energy at the end, after it has traveled a distance h, is going to be 1/2. Now, each of these objects is going to be moving at the end, so they will both have the same velocity. So we can write this as m1 plus m2 times v squared. So this is our linear kinetic energy. So again, we have to include this piece if we have objects that are moving. And then we have our pulley system that's rotating. So we have 1/2 I omega squared. And we actually have our one more potential energy at the very end, and that's going to come from m1gh, our gravitational potential energy, because our m1 will actually have a height after it's gone through the entire process. So, first things first, we want to combine our like terms. We have m2gh and m1gh, so that becomes m2gh minus m1gh, or just gh times m2 minus m1. And that's going to be on the left side of the equation. On the right-hand side, we see that we can replace our moment of inertia with the moment of inertia of a disk, which is mr squared over 2. And omega can be replaced with v over r, and make sure that value is squared. So really, this just needs to be cleaned up. This is a velocity squared here. So we can see on the right-hand side of this equation, we're going to have v squared. We can factor out from both pieces, this v squared and this v squared when I distribute that squared. I can also factor out a 1/2, and I'm left with m1 plus m2 plus mr, actually r squares will cancel out, divided by 2 is on the right hand side, and on the left hand side we still have gh m2 minus m1. And again, here we just need to get velocity all by itself. So that becomes 2gh m2 minus m1 all over m1 plus m2 plus capital M, which is the mass of our pulley, divided by 2. And then this entire thing has to be square rooted in order to get velocity by itself. Now, if you wanted to make this equation a little bit more general, you could leave the moment of inertia there, because sometimes you might have a rotating cylinder, you might have a rotating hoop instead. So if you left your moment of inertia I there instead, your final equation would have looked like the square root of 2gh m2 minus m1 all over m1 plus m2 plus I over r squared. So again, we got to this final answer because we did plug in our moment of inertia, assuming it was a disk, but sometimes it's easier just to leave moment of inertia there, get a general equation, and then depending on whatever object is actually rotating, we can substitute our moment of inertia at the end. Now, the final piece is to get our angular speed. Now, remember that angular speed is velocity over r. If this whole mess is our velocity, then we simply need to multiply it by 1 over r. And I'll go ahead and use the other version that I just wrote down. Over plus m2 plus I over r squared.